Hello मेरे प्यारे बच्चों, welcome back to another super quick revision explainer. I know, exams are just around the corner, but tension नहीं लेने का. We are going to make this chapter, work, energy and power, super simple for you. So let's get started.
First things first, let's start with a puzzle that confuses everyone. Picture this, a weightlifter. He's holding 150 kgs above his head. He's sweating, his muscles are shaking. We would all say, wow, that's a lot of hard work, Henna. But guess what physics says? He's doing zero work. Nothing. Est-ce que? To solve this mystery, we first need to understand what work really means in physics.
And this, bachon, is the first big confusion. You see, the word work we use in our daily life, like when you say, I have so much homework to do, is totally different from the scientific meaning of work. And understanding this difference is where you can save a lot of marks in the exam. In our day-to-day life, studying for an exam, that feels like a lot of work, right? Or pushing a wall with all your might, that's hard work. But in physics, for work to be done, two things must happen. First, you have to apply a force. And second, that force has to make the object move. There must be some displacement. So when you're pushing a wall, you're applying force, but the displacement is zero. So the work done is also zero. Ajeeb hai na? It's a little strange, but that's the rule. It all comes down to this one crucial formula. You have to remember this. Work, which is W, is equal to force, F, times displacement, D, times cos theta. Now that cos theta part is the real hero of this formula. It simply means we only count the part of the force that is in the same direction as the movement. Bilkul simple hai. And we measure it in joules.
So, this explains our weightlifter puzzle. Let's look at these 3 golden rules for when work done is zero. These are a favorite for 1-mark questions, so listen carefully. 1. Displacement is zero. Like pushing a wall or our weightlifter just holding the weight still. The weight isn't moving, so D is 0 and work is 0. 2. Force is 0. Well, that's obvious. And 3. The tricky one. When the force is perpendicular at 90 degrees to the displacement. You know cos of 90 is 0, right? The classic example is a coolie carrying a load on his head and walking on a flat platform. The force is upwards, but the movement is forwards. That's a 90-degree angle. So the work done on the load is 0. Remember these 3.
Okay, let's move on. Let's see how this idea of work is connected to energy. Think of them as being totally linked, you know? Just like your Instagram feed is connected to all your friends. If you do work on something, you are basically changing its energy. And the first type of energy we'll look at is the energy of motion. And that's kinetic energy, or K. Any object that's moving has kinetic energy. The formula is really simple. K equals half mv squared. Think of Virat Kohli hitting a cricket ball for a 6. The work he does with his bat gives the ball a huge velocity, right? And that velocity, the v, gets squared in the formula. That means a little more speed gives it a lot more kinetic energy, and that's why the ball just flies out of the stadium.
Now, for the most important relationship in this entire chapter. Basho, if you understand this one theorem, so many numerical problems will become super easy for you. I call this the master link, the key that connects work and kinetic energy. And here it is, the work-energy theorem. It's so simple, really. It just says that the net work done on an object, that means the total work, is equal to the change in its kinetic energy. So work is just a way of transferring energy. If you do positive work, you give it more kinetic energy. If friction does negative work, it takes kinetic energy away. That's it. Okay, let's use this to solve a typical exam problem. A raindrop is falling. So there are 2 main forces here. Gravity is pulling it down, doing positive work, and air resistance is pushing against it, doing negative work. The theorem says the total work, that's work by gravity, plus work by resistance, equals the change in kinetic energy. So first, let's calculate the work done by gravity, which is mgh. That comes out to be 10 joules. Then we find the change in kinetic energy using half mv squared, which is 1.25 joules. Now we just put it all together. 1.25 equals 10 plus the work by resistance. A little bit of math, and we find the work by resistance is minus 8.75 joules. See how the negative sign makes perfect sense? Air resistance removed energy from the raindrop. Okay, so kinetic energy is the energy of motion. But what about energy that's just stored, just waiting to be released? Think of it like the data in your monthly mobile plan. At the start of the month, it's all there, just waiting for you to use it. That's potential energy. We call potential energy V, and it's basically stored energy. The two most common types you need to know are gravitational potential energy, which is mgh, and that's the energy an object gets when you lift it up to a height. The other is spring potential energy, which is stored in a spring when you compress it or stretch it. Just think of a stretched rubber band or a water balloon right before you throw it. All that stored energy, just waiting to become kinetic. And now, we come to the ultimate rule of the game, a fundamental law that governs everything from a tiny apple falling from a tree to the huge planets moving around the sun.
This is the law of conservation of mechanical energy. It simply says that if you don't have forces like friction, the total mechanical energy, that's kinetic plus potential, always remains constant. Think of it like having 100 rupees. You can have it as cash in your pocket, that's your kinetic energy, or you can have it in your bank account using UPI, that's your potential energy. You can move the money between cash and bank, but the total is always 100 rupees. Energy just changes its form.
Let's see how this golden rule makes problems so much simpler. Look at this classic pendulum question. We need to find its speed at the lowest point. Forget about calculating complicated forces. Just use the rule. At the very top, all the energy is potential energy, mgh. At the very bottom, all of that has turned into kinetic energy, half mv squared. So we just make them equal to each other. mgh equals half mv squared. Solve for v, and you have your answer. It's that easy. Cello, just 2 more quick topics and you will be all set for the exam. We're almost there. So far, we've talked about how much work is done. Power is all about how fast you do that work. So power is just work divided by time. It's not just about doing the work, it's about doing it quickly. Think of a powerful punch in boxing. It's not just about force, it's about delivering that force very, very fast. That's why the other formula for power is force times velocity. More speed means more power. And finally, collisions. Here is the #1 rule you must remember. In every kind of collision, momentum is always conserved, but kinetic energy is the different story. In a perfect, bouncy, elastic collision, like with billiard balls, kinetic energy is also conserved. But in a real-world, inelastic collision, like a car crash where things get bent and stick together, some of that kinetic energy is lost as heat and sound. Okay, bachcho, we've covered all the concepts. Now for the most important bit, the final revision. Get ready to take a screenshot of this next slide. It's your personal cheat sheet with all the formulas. Here they are, all in one place for your last-minute revision. Work, kinetic energy, the work energy theorem, potential energy, conservation of energy, and power. Everything you need. And along with the formulas, here are some pro tips for me to help you avoid those common silly mistakes and score those extra marks. Always check the angle theta for work. Remember, negative work just means energy's being lost. The work energy theorem applies to the net force, the total of all forces. And for potential energy, you can choose the zero level wherever you want to make the problem easier. And finally, power is about the rate of work, so time is key. Okay, I'll leave you with a final challenge to think about. A question right from your textbook. A comet moves in an elliptical orbit. The sun's gravity does work on it, speeding it up and slowing it down. But why is the total work done by gravity over one complete orbit always zero? Think about what we learned today. All the very best for your exams, my dear students. You are going to do great.